Okay. Hello. So in this video, what we're going to do is talk about Haberman section 1.4, which concerns kind of these equilibrium or steady state solutions. Okay. And so the motivating question is, right, if you have like a one-dimensional rod or whatever other system that you care about, and you let just heat flow for long enough, okay, what is the resulting temperature distribution going to be? And so, of course, this depends on a lot of things, properties of the material, etc. And so for us, what we're going to do is focus on kind of this one-dimensional rod that we've been already working with. So the setup is as follows. So the PDE that we're considering is the heat equation. Okay, use a function of two variables, time and space, and we're also going to incorporate an initial condition, right? And we're going to say, here's what the heat distribution is at the start. Okay? And so you can zoom out. So we might draw this as that, right? That's how the heat's distributed. Maybe it's right, the graph of temperature above the line. And so turns out, in this case, we need a little more information. We need to know kind of what's happening at the boundaries. How much heat is being lost? Is heat being lost? Is there a prescribed temperature, etc.? So in addition to the PDE, as well as the initial condition, C, we also need to specify some boundary conditions, right? So one possibility is that we're prescribing the temperature at the boundaries, okay? And this temperature may depend on time. Maybe your rod is, I don't know, stuck into a water bath that warms and cools depending on the time of day, right? So it may depend on time, etc. Some other boundary conditions we can impose are, where is it? These kind of what mathematicians call Neumann boundary conditions. We interpret as kind of being a flux condition, right? And so in this case, we're specifying, right, what the flux or the flow out at the end of the rod is. For simplicity, I'm saying it's 0. These could be constants. These could be functions of time. Just depends. Okay? But we need to specify what's happening at the boundaries to make this problem a little better or more well posed, okay, to actually be able to get solutions. Okay, so as a starting point, we're going to assume that we have a prescribed temperature at the boundaries, okay? And we're going to make some assumptions about these prescribed temperatures. So the first possibility is that these prescribed temperatures, they don't actually depend on time, right? So they're going to be constants, or eventually they're going to be constant, okay? And so mathematically, we'd write this as, say, for the left prescribed temperature, in the limit, if you wait long enough, eventually whatever's happening there will converge to a constant temperature. And so then what we can do is say, well, let's just, wait long enough and then try to study the resulting temperature distribution, okay? So for us, in practice, we're just going to work with this first one. We're going to assume that the temperatures are constant, but you can kind of make this assumption, right, if the temperatures are not constant, by just waiting long enough and assuming that eventually the temperatures will be constant, okay? So the main object that kind of we'll be looking at in this kind of section are these things called equilibrium or steady state solutions, okay? And again, these are solutions that don't depend on, so we define these to be solutions that don't depend on time. One interpretation might be, again, wait long enough, okay? System will start to hopefully stabilize. And then the question is, what is the resulting temperature distribution once the system is stabilized? And so mathematically, we'd write this as, right, u of xt a priori, right? Our temperature may depend on space and time. but we're assuming that because it's a steady state or it's in equilibrium, it doesn't actually depend on time, and it just depends on space. Okay? And like I said above, for these problems, we'll primarily assume that the temperatures, the prescribed temperatures at the boundary points, those are fixed. Okay. So here I've written, right, U may depend on space and time, but this is just to fit into the framework of the general, PDE, initial condition, boundary conditions. Okay. Because yeah, the solutions that we're looking for, these variables won't play a role. Okay, so in this case, what happens? Well, we're saying that U doesn't depend on time. Okay, so how does U change with respect to time? Well, it's not going to change. So that's where that 0 is coming from. Okay. But because of the heat equation, we have this equality, right? Change in time is some constant times that second spatial derivative. Okay. So kind of bringing things back together, the differential equation that we end up with is this, right? 0 is equal to some constant times the second derivative of U, okay? And notation, right? I've written a non-curly D because, right, we're assuming that U only depends on one variable. So it's an ordinary derivative. Okay. Okay, so we've simplified the problem. Now the question is, right, what are the solutions to this differential equation? Okay. Maybe think back to your time in ODEs, come up with it in your head. And so it turns out all the possible solutions to this differential equation are just linear functions, right? You have some constant plus a constant times the spatial variable. Okay. Okay. Right, so if we're looking for equilibrium solutions, we have a much simpler expression, and we have an expression for what the solution might look like. Okay. So now the question is, right, well, what are these two constants? Okay. Again, maybe think back to your ordinary differential equations, right? How do we kind of fix the constants for an arbitrary solution for an ODE? Well, we need to incorporate boundary conditions, initial conditions, some extra information about the problem. Okay, and so in this case, it's the boundary conditions that are going to tell us what these constants are. Okay. So if we start writing things out, okay, U of 0 in this case is equal to T1, right? So the value of U at the left endpoint is our prescribed temperature, and this is coming from the boundary condition. Okay, but we also know that U of 0, right, the value of U at the left endpoint is this constant C1. Okay, and this is coming from the form of our solution, right? What we had back up here, U is C1 plus C2x. Okay. So putting these together, we conclude that, well, C1 is equal to T1. Okay, so we fixed one of the constants, and we fixed it using the boundary conditions. Okay, so what else? Well, we also have information about the right endpoint of the rod at x equals L. Again, so U of L is equal to T2. This is from the boundary condition. We also can say that U of L is equal to T1 plus C2L, and that's coming from, well, one, right, from the form of the solution function. Two, it's coming from what we already discovered up here, right? Right, so taken together, T2 is equal to T1 plus C2L. Bring things together, we get that the second constant is going to be the temperature difference between the two endpoints divided by this, you might call like a scaling constant, L. Okay. Okay. Okay, so bringing all of that together, then what we can do is say, well, right? Just plugging in for what we found C1 and C2 to be, the steady state solution or the equilibrium solution with what mathematicians might call Dirichlet boundary conditions, physicists might call prescribed temperature boundary conditions. The form of the solution we get is exactly this. So U of X is T1 plus T2 minus T1 over L times X. Okay? So it's a linear function. The interpretation would be, and we're going to draw pictures in a second, right? If you wait long enough and you have prescribed boundary temperatures, right? If you wait long enough, what's the temperature distribution going to be? Well, it's just going to be a line from your left temperature up to your right temperature, or right, depending on the sign, depending on whatever. Okay. Okay, so this we said is what happens, right, if we assume that U doesn't depend on time. But what we can show more generally is that, well, if U solves, right, this heat equation where U does depend on time, okay, and so again, this is our PDE telling us how U changes. This is our initial condition telling us what the initial temperature distribution is in the system or in the rod. And these are our boundary conditions telling us what the temperature is at the two endpoints. Okay. So generally, if U depends on both space and time and it solves this, this problem, then what we can say is that if you wait long enough, the temperature distribution is going to converge to an equilibrium solution, and the equilibrium solution is exactly going to take this form. Okay. And so this is not something that we'll cover in this course, but it is covered later in Haberman's textbook. Okay, so I promised some pictures. So what does all this look like? Well, we have a few of these kind of, I don't know, empty graphs, okay? And so as written, so what we're going to do is we're going to ask, well, at time 0, at time 10, and at time 100, right, what's happening with the system, with our temperature distribution, okay? And so what we've done is we've prescribed a temperature at the boundaries, and that's how I've indicated these. Okay, so whatever our solution does, it has to take those values at the endpoints. Okay, and so the one thing missing here is an initial condition, right? What is the initial temperature distribution? Just draw it like that. Okay, so then the question is, well, what happens through time? Now, Fourier's law of heat flow, heat conduction, whatever it was called, is that, well, heat's going to flow from places of higher temperature to lower temperature, okay? So what we'd expect is that this bump, right, this high temperature here relative to its surroundings, this is going to decrease, okay? Likewise, this valley right here, it's a lower temperature relative to its surroundings, so heat is going to flow from nearby into the valley. So this is going to increase, okay? So if we let heat flow for a little bit, well, we might get something like that, okay? So peak is decreased, valley has increased, but the prescribed temperatures are still there, okay? Keep going, let the system flow for a bit more. What's going to happen? Well, eventually we expect a straight line connecting the two temperatures, okay? And that's what we computed a second ago. Okay. Okay. So that's what happens if we have, right, fixed temperatures or prescribed temperatures at the endpoints. Next question is, well, if instead of prescribing the temperatures, what if we prescribe something about heat flow? Okay. And so in this case, what we're going to do is we're going to, so revisit the same differential equation, right? Heat equation, initial condition. I think I wrote them here. Yeah. heat equation, initial condition. But now for the boundary conditions, we're going to consider this setup. Let's go back in, where we're saying that the heat flow at the left endpoint is 0. It's an insulated boundary. No heat is coming in or getting out of our system. Likewise, at the left endpoint, L, there's no flow of heat. Okay. So very similar problem, slightly different boundary conditions. Now the question is, how do these different boundary conditions, right, specifying flow instead of temperature, how does this change the behavior of our solutions? Okay, so what we're going to do first is just ask, well, how do we interpret these boundary conditions? Right? I said, 0 flow, so physically, that's what's happening. Mathematically, how might we interpret this? Well, so I've drawn a few arrows here. So the interpretation here is this black arrow and this black arrow. These correspond to the same kind of boundary condition pair, right? 0 flux at the left, 0 flux at the right. Okay. This blue pair here is another 0 flux to the left, 0 flux at the right. Green is another pair, 0 flux at the left, 0 flux at the right. Okay. All of these pairs of 0 flux at the boundaries correspond to different initial conditions, right? So this pair of black boundary conditions, those might correspond to, there's something missing, the piece is missing, but they'll be filled in a second. These two 0 flux conditions, they might correspond to either this initial condition or this initial condition, right? The important thing is that the derivative of the temperature profile, the boundaries is 0. Okay. Another possibility is this. So we have 2 other possibilities for blue and 1 other possibility for green, right? Black, blue, and green, the initial conditions that we've drawn in here, right, are all viable initial conditions for the same, right, boundary condition of 0 flux. Okay? And so maybe the takeaway here is that maybe the picture is you have these 2 derivatives at the endpoints, and these are allowed to move up and down however you want. It's just where they are fixed, kind of height-wise, depends on the initial condition. Okay, depends on how much heat is going to flow out, or I guess not flow out, but they depend on the initial condition. Okay. Let's see. So, okay. So how do we solve for a steady state solution with these boundary conditions? Well, I've written the problem on the left. Okay. And so again, we're looking for a solution such that the time derivative is 0. We saw above that such a solution must take this form. Okay. And so if you take the derivative of this function with respect to x, right, C1 is a constant, so that's going to fall away. What we're left with is this x derivative is equal to C2. And I guess I should have written here, these should be non-curly Ds, but whatever. Okay. Okay, so let's play the same game. So the boundary condition right here, right? I've just copied it down here. You can say that's from boundary condition. But we also know that the derivative of u at x is equal to C2, and that's coming from the form of the solution function, okay, or from the solution function. Likewise, right, if we look at the other endpoint, turns out we get the exact same condition. Okay, This is from the boundary condition. This is from the form of the solution function. Okay. So what do each of these tell us? Well, both of these boundary conditions tell us that whatever this constant C2 is, that has to be 0. Okay. And so going back up, right, from the form of the solution, C2 was attached to X. Okay. So if this is 0, then U of X has to be a constant. Okay. And so that's what's written down here. U of X must be a constant, C1. And similarly, right, from before we said, well, in general, if you have, a solution that depends on time and space, and you let heat flow long enough, or you let the system run long enough, eventually you'll converge to a steady state solution. So for these boundary conditions, you get the same exact thing. Okay, let your system run long enough. What happens? The temperature distribution will approach a steady state or an equilibrium, and that equilibrium is going to be some constant C1. Okay. So what do these look like drawn out? Well, over here, we have kind of the boundary conditions, right, which we've drawn as these derivatives, these zero derivatives, or these tangent vectors at the endpoints. And here's our initial condition. Okay, so again, heat is going to flow from high temperature to low temperature. Okay, and so this valley should rise as well because heat's going to flow into that valley relative to the surroundings. But now what's interesting is that we're not prescribing temperature at the endpoints, right? We're just describing zero flow. Okay, so because the temperature right here is lower than the temperature up here, we expect heat to flow down. So what ends up happening is if you let the system run for a little bit, you might get something like this. Okay, this valley has filled in a little bit, heat's gone in there, so kind of the temperature has risen right there. Heat's flown out of this peak, so that peak is decreased. But because this temperature was greater than this temperature, right, where this tangent arrow is stationed has gone down a little bit. And so that's kind of what I've drawn there, right? That arrow has gone down. Likewise, this temperature is less than that temperature, so this arrow goes up. And so we get the profile in the second spot. Okay. Finally, let the system flow for more. Okay. Heat's going to flow down from there. This is going to go up a little bit. This might stay roughly the same. This is going to increase a bit. And in the end, we'd expect a temperature profile like that. Okay. Which is what we computed just above, right? Equilibrium solution should be a constant. Okay. Okay, so, right, one question then is, well, right, we have an arbitrary constant. Can we compute what that constant is? And generally the answer is yes. Okay, right, so one thing to note, because there are no sources, right, heat's not being generated or spontaneously taken away from the system in the interior of the rod. So because there are no sources, and because there is no flux or heat loss at the boundaries, okay, we'd expect that the total thermal energy and the total temperature to be conserved, right? We shouldn't be losing anything. Okay? So written out mathematically, right, or maybe symbolically, what is this equilibrium solution, right? It's going to be a constant. What's the constant? This expression right here is a total thermal energy or total temperature, total quantity of interest at the start. Okay, and again, because there's no heat lost to boundaries, because there's no source or heat gained or lost spontaneously within, whatever the thermal energy is at the start, that should be throughout all time. Okay? And so this f of x, what is this function? Well, that's the initial condition. Okay. Yeah. So the book gives a bit more in-depth details as to this. And I'll talk about this a little bit in class. But otherwise, this is the content of section 1.4, talking about these equilibrium solutions and making sense of them.